So today's topic is Introduction to Current Electricity, one of the topics covered in Senior 4, the first term. So all my candidates, you're really welcome, and I ask you to pay attention, kindly be observant, and try to learn something from this tutorial. And just in case you have a query, kindly leave it on the comment section. So the competency is: learners should appreciate that electric current is the transfer of charge through a conductor, either by electrons or by ions. So we need to appreciate that throughout this discussion. We should be in position to now understand that what brings electric current is actually the flow of charge through a conductor. So as the charge is flowing through a conductor for a given time, and then that constitutes what we call current electricity, and this charge can be an electron or an ion. Learning outcomes or the objectives. The learning outcomes. So by the end of this topic, the learner should be able to: 1. Understand what EMF is, electromotive force. So understanding should be here. B. Understand that cells convert chemical energy into electrical energy, producing current, and also the force needed to create a flow of current in a circuit, the EMF. Understand that electric cells are very useful but have their limitations. At some point, they do not make it throughout. In other words, they have boundaries, or they have the limitations. The learner should be able to understand the nature of electric current, its source, what makes it flow around the circuits, and how it is measured. Which device do we use to measure current vis-a-vis the voltage? Know that some materials are electrical conductors and others are actually insulators. And then recognize, understand, and apply the knowledge of series and parallel circuits. So the arrangement of appliances in the house, arrangement of resistors, arrangement of all electrical gadgets. We need to get to understand the two cases, that is the series and the parallel. However, we can still combine them parallel series or series parallel depending on the demand of the task. Should also be in position to appreciate the circuits. Appreciate that circuits may be represented as circuit diagrams, considering, in other words, consisting of an agreed set of symbols to represent components. So by the end of the day, we should be in position to understand the symbols that we use in the discipline electricity, or in this chapter electricity. So we have very many symbols and we use them as per the demand of the scenario. So basically, those are the few learning outcomes that we shall hijack throughout this topic, Introduction to Current Electricity. So the suggested learning activities, what a learner has to do in order to achieve the outcomes, in order to achieve the competency. In groups, taking it as a case where learners are learning, but are they actually exploring this in their groups? Learners revised prior learning about electricity using the prior information we have right from primary, what electricity is. Carry out research and explain using annotated diagrams. So we should get back and make research on that. The structure of a simple cell and how chemical reactions can produce electricity. The flow of electricity around a circuit, powered by an electric cell in terms of both the current and flow of charge and the potential difference created by the cell. In pairs, learners brainstorm, research, and report on the following one: common practical applications of electric cells, recent advances in cell technology, applications for which cells are not appropriate and the reason as to why, and then other sources of EMF apart from the simple cell. It is not only the simple cell that gives electromotive force. We have other sources of electricity, and throughout this tutorial you should be in position to hijack some and also make personal research on that. In pairs, learners research and use diagrams to explore and explain the symbols used in a circuit diagram and the differences between series and parallel circuits, vis-a-vis the advantages and disadvantages of these arrangements. So we should be in position to do that, and just in case a task is requiring us to make a recommendation for which kind of or which the type of arrangement we should propose, and then after this tutorial you should be in position to perform vivid calculations and be in position to make a recommendation whether the item at hand needs to make a recommendation on a series arrangement or the parallel arrangement. Investigate and report the relationship between voltage and the brightness of the bulbs. What happens on the brightness of the bulbs every time we increase the number of dry cells? In other words, the voltage across it. I think the brightness increases, and we shall discover the logic behind that. Explain the practical implications of this relationship. Practically, what does it imply? In groups, learners plan and report on an investigation using an electric circuit with batteries and bulbs to explore the electrical conductivity of different materials such as copper, wood, plastic, iron, aluminium, graphite, rubber, cardboard, glass, wool, etc. We shall get to realize the level of electrical conductivity of each material here. In groups, learners plan and report on an investigation using batteries, bulbs, and an ammeter to measure the current flowing through different parts of series and parallel circuits, and then explain why domestic circuits are in parallel. Why do they prefer parallel arrangement? So throughout this discussion, you should be in position to explain that. Learners research and contribute to the presentation. To explain how electric current involves the transfer of a charge by electrons or ions. So basically, that is what you should be in position to know for you to be in position to acquire those learning outcomes, or to portray those learning outcomes, and at the same time to achieve the competency of the topic. And just in case you are to be assessed, then the competency must be a key factor here. Current electricity. Current electricity is the flow of charged particles from one point to another. For example, electrons. So once electrons start to flow from one point to another in a conductor, and then on the other hand, current is actually generated or is also flowing, though in the opposite direction. Electrical devices which use electricity are called electrical appliances. The fridge, the television, the woofer, name them. Sources of electricity. or the electromotive force include batteries, generators, solar panels, or solar energy, windmills, etc., dry cells, etc. Name them. So the terms used in electricity, there's a charge. This is a quantity of electricity which passes any point in a conductor. And the SI unit is coulomb. So electric current is also another term. Charges move from one point to another in a given time. And this rate of flow is called electric current. So current is the rate of flow of a charge. So as charge is flowing from one end of a conductor to another end, it is doing this in a time interval. So if you estimate the rate at which it is flowing, then you are actually determining the current. Definition. Electric current is the rate of flow of charge in a conductor. And the SI unit is ampere. So let's consider this circuit whereby you have a single dry cell, and when it is closed, then it's a complete circuit. For a complete circuit, we can see currents flowing as a result of electrons flowing from negative to positive, as current flows from positive to negative. Taking a circuit of this caliber, we have a battery, copper wire, connecting wire, light bulb, and the switch. And what is the importance of the switch here? Is to set on and off the circuit, and also the battery is to provide the source or the EMF. Then the bulb is to give the manifestation of this current. So as we can see, when the switch is on, electrons flow from negative to positive. Electrons flow from from negative to positive. When the switch is on, electrons flow from negative to positive. This is because the electrons are free to motion. So the electrons on the outermost shell of the conductor, taking a copper wire, they are free to mobility. So as they are flowing through a conductor, they constitute the flow of current, because we have realized that the rate at which electrons flow determines current. So the switching on and on sets what we call a closed and an open circuit. As you can observe clearly, that when you switch on, electrons flow at the same rate current flows. That's why the bulb gives light. Electrons flow as the current also flows, giving light. So the setting on and off brings about the flow of current through the bulb, and hence giving that bright light. So energy is being transformed here. From the cell, it is chemical, electrical, which is electricity, and then to the bulb, what we call the light energy. So there are very many energy changes that take place within a closed circuit where battery and an appliance like bulb is connected. So setting on and off brings the flow of current. Otherwise, let's move to the next page. So the dry cell. So I will borrow some chemistry that you have, and we need to share the logic behind the operation of a dry cell. How chemical energy is converted to electrical energy and hence applied to the appliance. And for the case of a bulb, then that is light energy. For the case of a heater, then that is heat energy, etc. Can we understand this, please? The simple dry cell. Let's watch this video. So that is a simple dry cell, a unit of making electricity. Considering a circuit of this caliber, we see that current, for instance, is flowing from positive to negative, giving light on the bulb, as long as the switch is on. Then when we arrange two cells, then we form what we call a battery. Then we shall have more positive and negative. And this is the logic behind a dry cell. So when acid dissolves in water, they form ions, which are positively charged and negatively charged, what we call cations and anions, forming what we call electrolytes. Taking a consideration where a zinc rod is immersed and also a copper rod immersed. So the zinc will attract the negatives and become an anode, negatively charged, and the cathode will attract all the positives and become positively charged. When a bulb is connected, we actually see light on the bulb, meaning electrons will start to flow from negative to positive at the same rate current flows from positive to negative. So the logic behind this was set by the French engineer Georges Leclanche in the early 1866, who invented the battery that bears his name. His invention was quite heavy and prone to breakage, was steadily improved over the years, and this was done by actually the modified type of a battery was modified and it's now called the dry cell. The dry cell. However, in the early 1866, Carl Ganza of Mainz, who is credited with constructing the first commercially successful dry cell, the zinc dry cell, in other words, the zinc dry cell carbon cell. Once again, so that was in 1881. 1881, Carl Ganza of Mainz, who is credited with constructing the first commercial successful dry cell after George L. That is in the early 1881. He also invented a dry cell that was out of zinc carbon. Then the variation followed by 1889 and so on. So this is a dry cell. The dry cell is a modification of the wet George Lincoln. As you can see, for us to examine this dry cell, we need to check the internal part of it. We have an electrolyte, or the graphite rod, which acts as a positively charged rod, and then the zinc container acting as the negatively charged rod or charged part, then ammonium chloride jelly that has to solidify or liquidify with water to form these cations and anions, to form the cations and anions. Then we have the carbon washer, we have the pitch, we have the terminals, the positive and negative terminals. We have the insulating thick paper to cover the internal part of the dry cell, the brass nut, which is giving us a positive, and then the negative on the carbon black word. So the chemistry behind this is as a result of oxidation that takes place between or at the zinc cathode, where the zinc gains excess electrons, and these electrons increase the number of negatively charged particles on the zinc cathode. So the process goes to the reduction at the graphite anode, and this gives a modification of a dry cell. As we can see, we have different types of dry cells. There are this kind of small one used in watches. They are called the mercury or zinc button cells used in watches, calculators. So we have very many types of dry cells depending on the requirement or the demand. We have the nickel cadmium cell. This one is used in the TV remotes, used in torches, small torches, and so on. So what I will task you is to sit down, draft some literature on the parts of a dry cell, and give the importance of each part. Kindly sit down and make research on that, and then basically explain how mechanical energy is converted to electrical energy, and this, well, you will find it in the subsequent presentation, but still I need you to sit down and draft some literature on that. Draft some literature. Basically, I've been showing you a video that gives you a clarification on the internal parts of the dry cell. So the current we agreed is the rate at which charge flows. So that's what we get as charge over time, and that will be Q over T. So this is one of the first calculations, or I mean the first equations that we should memorize or understand, and we shall use this very in this context as far as calculation of current, calculation of charge, calculation of time are required. Note, the time should always be in seconds. Of course, that is the song of the day as far as physics is concerned. Current is measured by an instrument called an ammeter. Now we need to define the SI units of these variables, the ampere, the volt, and so on. So an ampere is the constant current when a charge of 1 coulomb flows in a conductor in 1 second, as simple as that. So if a charge of 1 coulomb flows in 1 second, then there must be a constant current flowing, and that is ampere. Or another definition, an ampere is current which, when flows in 2 straight parallel wires of infinite length placed 1 meter apart in a vacuum, produces a force of 2 exponent negative 7 Newton per meter on each of the wires. This is quite advanced, and my people in HSC, this is one of the definitions that we appreciate, except those of lower secondary. You can use the first definition, as in when a charge of 1 coulomb flows in a conductor in 1 second, then there is a constant current. But also Q is equal to IT, meaning from the first equation I told you, when I make charge the subject, I just multiply both sides by TT, then I get charge is equal to current times time, implying that 1 coulomb is equal to 1 ampere times 1 second, as per the units. Now, definition, a coulomb, because we agreed a coulomb is an SI unit of charge. A coulomb is the quantity of charge which passes any point of a conductor in 1 second when a current of 1 ampere is flowing in the conductor. So once we get a current of 1 ampere flowing through a conductor, then the quantity of charge that passes through that point in every 1 second is what we call a coulomb. Other units of current include milliampere, and that is converting it to ampere with times 10 exponent negative 3, microampere times 10 power negative 6, to ampere. So basically that is it. Let's move to the next. Calculations. Let's try these calculations. Here we are given current, time is given, then they want us to calculate charge. We use the first equation. Substitute, get the answer, and the charge will be 43,200 coulomb. Item number 2, we can see that the charge is given, time is given 25 minutes, we have to change that one to seconds. They want us to find current. So if the coulomb is given, I mean the charge, time is given, we take it to seconds. We use the first equation, substitute where necessary, make I the subject, which is the current, divide both sides by the time, and we get 1 ampere. So 1 ampere will flow in a conductor for a period of 25 minutes, and every time it flows, it means that a charge of 2,550 coulomb is also flowing. A current of 6 milliampere, we agreed this into ampere becomes 6 times 10 power negative 3, flows for 2 hours in a circuit. Find the quantity of the charge. Very easy. We substitute in our equation. We agreed change this milliampere into ampere by multiplying it by 10 power negative 3. And then on substituting everything, we are getting our charge as 43.2 coulombs. Another item or question, activity or example, a charge of 20 kilocoulombs crosses 2 sections of a conductor in 1 minute. Find the current through the conductor. Now we need to first change these kilocoulombs to coulombs. That's times 1,000, and then we shall have 20,000 coulombs, and the time goes to seconds, and that will be 60 seconds. Since 1 minute is equal to 60 seconds. On substituting in our first equation, I told you the first equation is very crucial and important. Substitute, get the answer of ampere, the answer of current as 333.33 ampere. The potential difference, what we call the PD. And then we shall have a discussion on the difference between a potential difference and the electromotive force. We tend to confuse these two things, and then by the end of the day, you find yourself using the definition of an EMF as the potential difference. However, they are totally different. An EMF or electromotive force is different from a potential difference. So how do we define a potential difference? This is the work done in joules when 1 coulomb of a charge moves from one point to another in a circuit. If 2 points in a conductor of different electric potential, then the charge can move from one point to another and work is said to be done. Potential difference is sometimes referred to as voltage. Very correct. And the instrument used is called the voltmeter. And the SI unit is volts or volt. Now, once there is a potential difference between 2 points on a conductor, in other words, when you have a positive and negative on the ends of the conductor, then you've created what we call a potential difference. For that case, a charge is in position to move. A charge is in position to move from negative to positive. So one charge of a coulomb moving from one point, that's from a negative to a positive in a circuit, for that case, there must be work done for it to move. And that work done, if it is measured in joules, that is what we call the potential difference. In other words, the energy required to push to transport 1 coulomb of a charge from one negative terminal of the dry cell to the other positive terminal of the dry cell. So we measure this using a voltmeter, and the voltmeter measures this still in the standard units of volt. What is a volt? This is the PD between 2 points in a circuit. when 1 joule of work is done to move 1 coulomb of a charge from one point to another. So what we should make constant here is a unit. A unit means 1. So if it is work to be done, it should be of 1 joule. And then if a charge is to move, it should be 1 coulomb. A charge of 1 coulomb, then it should move from one point to another in that conductor. So that's what we call a unit volt. Then the electromotive force. What is an EMF? Here we agreed work is done to transport 1 coulomb of a charge from one point to another. And this is because of the difference in the electric potentials at the ends of this conductor. Electromotive force. This is the work done in joules. When 1 coulomb of a charge moves from one point to another in a circuit, in a cell, in a circuit in which a cell is connected. In which a cell is connected is missing here. In a circuit in which a cell is connected. Now for us to have electromotive force, you must have a cell. Now the work will be done on transporting still 1 coulomb of a charge. For it is moving still from one end to another in a circuit in which a cell is connected. Shall discover this in the video. They still share the same units. So the sources of EMF, we agreed: cells, batteries, etc., generators, solar cells, etc. Now let's watch this video and we get the difference between potential difference and electromotive force, and also how current is in position to flow through a conductor, as they claim is as a result of flow of charge or electrons. So in a conductor, I have free mobile electrons that are in zigzag or random motion, as you can view the video. These electrons, before applying a potential, they are at random motion. But on applying a voltage, they are aligned and they start to flow in a single direction. As you can see, applying a voltage, they align. Now they start to flow in a single direction, as you can see, from negative to positive inside the conductor. And this voltage is the one that requires or that calls the flow of current. Force, because of which free charge particles move, that is the voltage. So when the charged particles move from one point to another, then the force that moves them is what we call a voltage, or the work done to move them. Let's look at this, considering a situation where we are trying to design a dry cell, where we have the copper rod, the zinc rod immersed in dilute sulfuric acid. So the chemical action is taking place inside the sulfuric acid. So the mechanical energy is to be converted. As a result, copper loses electrons and then becomes excessively positively charged, and then the zinc acquires the electrons, and then the zinc becomes negatively charged. So by so doing, a potential difference is created. So the copper rod will be negative and the zinc positive. So you can see the potential because of the difference in the terminals. Difference in the terminals creates a potential. So because of dilute sulfuric acid creating a situation of a dilute material, these charges do not neutralize. They do not combine and neutralize. So they maintain that potential difference. because of the variation of the voltage at each stage, or the variation in the electric potentials at each end. So when we connect any appliance, we get to realize that there is a potential energy, or the work done is required to transport this charge, this electron, from negative to positive. And then at the copper rod, the process of losing electrons is maintained, and it's acquired by the zinc. So the process continues as long as the circuit is still on. So negative electrons or electrons are lost by the copper rod, gained by the zinc, and because of the potential difference, they flow from negative to positive. So this process continues as long as the circuit is still on. And then 2, the dielectric or the acid does not allow the neutralization of these charges, as it does not allow these electrodes to merge. So that's how the process takes place inside the battery. For that case, you can see that the potential difference is in between the terminals. Now, the force that pushes these electrons from this copper rod to the zinc rod is what we call electromotive force. It is inside the cell, and it's trying to separate these electrons from the positives on the copper rod. Meaning, without an EMF inside the cell, then we do not have a potential difference. Because, as you can see, the negative charges are separated by that force that pushes them to move from the copper rod to the zinc. So that's what we call electromotive force. Electromotive force. So the mother of potential difference is electromotive force. Electromotive force, the EMF. So we first have an electromotive force before we get a potential difference, and then finally we get what we call current. Current, because potential difference brings charge flow, electrons moving from negative to positive, and the process is maintained as it gives a manifestation of current. So basically that is how the battery still works. Any question? Please leave that question on the comments. Internal resistance of a dry cell. This is the opposition of flow of current within the cell. We agreed that inside the cell, electrons are sent to the zinc plate or rod as a result of electromotive force. Meaning, the force experiences resistance. So within the cell, there is that opposition subjected to that very force that sends the electrons from the positive terminal to the negative terminal within the cell. So that opposition is what we call internal resistance of the cell. On the other hand, electrical resistance, this is the opposition subjected to the flow of current in the conductor. In the conductor. We agreed on a conductor. Inside the conductor we have electrons, but these electrons are at state of free mobility, and then when they are subjected to the potential difference, they flow, but as they are flowing, they actually lose their energy on collision with the atoms and the electrons themselves. So that reduction, or that brings the reduction in their speed, and that manifests as electrical resistance. The other unit of resistance is ohm, and then the definition of an ohm is basically the resistance of a conductor in which current of 1 ampere flows when a potential difference of 1 volt is applied across its ends. When you apply a voltage or a potential of 1 volt across the ends of a conductor, and then you allow current of 1 ampere to flow through it, for that case, the resistance subjected to that current in that conductor is measured and it's actually recorded as an ohm. Factors that affect resistance of a conductor. There are many factors, and among which some of them shall discuss them here. We have the length, L. So resistance of a conductor is directly proportional to the length of a conductor. As you can see, R is directly proportional to L. This vividly shows that when you increase the length of the wire, then you automatically increase the resistance of a conductor. On the other hand, when you reduce the length, then you actually mean to reduce the resistance. Why? This is because an increase in the length creates a longer distance of travel, of drift of these electrons. So the electrons continuously lose their energy while drifting in a longer or through that long wire. So in the subsequent time, few or less amount of current is registered. So this is as a manifestation of higher resistance. On the other hand, a shorter wire has a shorter distance of drift. So electrons within no microseconds are already at the end side of the conductor. So for this case, a significant value of current is registered, meaning the resistance to this current is low. Resistance of a conductor increases when its length increases. Therefore, the shorter the wire, the lower the resistance, and the longer the wire, the higher the resistance. Very clear. Roman 2 or part 2, cross-sectional area. How does cross-sectional area affect the resistance of a conductor? The resistance of a conductor is inversely proportional to its cross-sectional area. This one means that when you increase the area, you're reducing the resistance. And when you reduce the area, you're increasing the distance. So thin wires have a higher resistance, while thicker wires have a low resistance. Why do you think so? That thin wires have a higher resistance, while thicker wires have a low resistance. We agreed? Reducing the area increases resistance. Why? This is because the mean free path of electrons reduces with a reduction in the cross-sectional area. So a few electrons drift within that wire, signifying less current. In other words, implying high resistance. The moment you experience low current, it means higher resistance. So anything that brings higher resistance reduces the current. On the other hand, increasing the cross-sectional area, you reduce resistance. Why? This is because you've created a bigger space for electrons to drift, to flow. So for that case, a significant number of charge will be registered to the other end of the conductor within no minute, and then they register a bigger value of current, meaning low resistance. Temperature. The resistance of a pure material like copper increases when their temperature increases. I repeat, pure metals. But do you have pure metals in life? Well, let's take copper as a pure metal. Increases with the increase in temperature. Why does temperature affect the resistance of a material? Check here. Inside the copper wire, we still have these free mobile electrons. As we observed in the previous video, that these electrons are in random zigzag motion before applying a PD. On applying a PD, they drift in a single direction. I mean direct current for that case. But before even applying a potential, increasing just the temperature implies kinetic energy of implies an increase in kinetic energy of the electrons inside the material, and also implies increase in collision, the rate at which these electrons collide. Remember, collision reduces the drift velocity of these electrons, and once the drift velocity of electrons is reduced, then resistance of the material increases, and for that case, low current is registered. Nature of the material: good conductors. These are materials that allow electricity or heat. For the case of heat, heat to flow through them, and then electricity, of course, electricity to flow through. And the nature here is that they have low resistance compared to bad conductors. Why? Well, for them, they have free mobile electrons, and what brings current is that the presence of free mobile electrons. Once they are not interfered to the climax, then bad conductors, actually, for case of insulators, they actually do not allow heat or electricity to flow through them. This is because they do have electrons, but their electrons are firmly packed. In other words, their atoms are firmly packed that electrons do not flow through them. And since we are appreciating that what brings current is flow of electron, then for that case, we shall not have current because electrons do not flow. Then semiconductor, these are materials that behave as conductors and on the other hand as bad conductors or insulators. In other words, they share the properties like silicon. Note, the first two factors can be combined as that, then we get the parameter called resistivity measured in ohm meter. Because you agreed that resistance directly proportional to length and also resistance inversely proportional to area. Combining the two, we get what we call resistance directly proportional to length and also inversely proportional to area. And removing the proportionality symbol, we replace it with a constant of proportionality, for this case termed as resistivity. Resistivity. Now let's watch this video and we expand our understanding on these factors. So as you can see, we have a shorter wire and a longer wire. What is the significance behind this? Let's take a situation where I have a rod, a straight rod, with one rod with humps and the other one, or roadblocks, and another with the, let's split this, another one with what? So the flow of current is in such a way that when resistance is not there, it just flows. Taking a situation where I have a roadblock on the road or humps on a road, this lowers the speed of travel of cars due to those blocks. Now the man behind all this is Ohms, who set the perimeter connecting resistance, voltage and the current, and was named, the SI unit was named after his discovery or after him. So the length of the conductor, cross-sectional area of the conductor, type of a material, temperature, we discussed them there. Let's just watch how they affect this resistance of the material. This experiment was done by Ohm. So let's look at the length of the wire. Increasing the length increases the resistance as the electrons travel a long distance. Imagine a water pipe of that caliber. Let's first repeat this. So imagine a water pipe. The longer the pipe, the harder it is for water to flow through, right? That's true. The same thing happens with electricity. More resistance, less distance, longer of the wire, length of the wire. So longer wires have more resistance because electrons have to travel a longer distance, and the other one have less resistance because electrons have to travel shorter distance. Inside the material, we can see electrons hovering, colliding with the atoms, colliding with themselves. And then for this, as the electrons travel a distance of 6 meters, they actually reach the other positive terminal when they have lost the biggest percentage of their energy. But for the 1 meter, they actually do not lose. They reach with their original energy. Is it true? Anyway, as you can see, so it is so significant that resistance increases with the increase in length, and then a reduction in length reduces resistance. So length of the conductor is directly proportional to resistance, or resistance directly proportional to length. Cross-sectional area is the next thing. Cross-sectional area. So this one is of length 6, but now the diameter, they do have different diameter. Check on this. Comparing this, when you have a wider road, very many vehicles pass, and then when you have a smaller road, a few vehicles pass on it. It is the same with a conductor. The bigger the cross-section area, many electrons flow, and on the other hand, few electrons flow. So that's why we get a situation where resistance is inversely proportional to cross-sectional area. Type of the material: copper is the best, followed by silk and iron. And we can investigate this in our lab using the same gadget and discover how current, or the intensity of, or the brightness of the bulb. The insulators, we can see rubber, wood, ceramics, glass. They do not actually conduct electricity. That's why we use them as insulators to cover these connecting wires. Why? Because they do not allow current, electricity to flow through them. The nature of the material, we agreed that they affect resistance. I think insulators have higher resistance. And then copper wires have relatively low resistance as long as the temperature is kept constant. So combining the two equations, we get this direct and inverse proportionality. Removing the proportionality, we get resistivity. So this is the factor that brings resistivity, as R is equal to resistivity times length over area, where R is resistance of the material, length of the material, cross-section area. The constant of proportionality, known as the resistivity of a specific wire, measured in ohm meter. Measured in ohm meter. The A levelers, you know what we are talking about. Thus, the resistivity of a conductor is defined as the resistance of the conductor of unit length and unit area of cross-section. When area is 1, length is 1. So the resistivity subjected by this material is a unit called resistivity. So the SI unit is ohm meter. The SI unit is ohm meter. The SI unit is ohm meter. The calculations are there. However, we are getting to most of them in this calculation. We can see the length is 5 meter, cross-section area is 2 millimeter. We have to convert that one to meters. Resistivity is given 1.7. We convert everything to standard units, to SI units. Then we calculate the resistance of the wire using the first equation of resistivity. Substitute everything in the first equation, where R is equal to resistivity times length over area. So the response, after substituting the perimeters, 5 meters, 2 times 10 power negative 6 meters squared, that is the area. And then resistivity 1.7 exponent negative 8 ohm meter. I can see the meter crossing. We remain with resistance measured in ohms. Resistance measured in ohm. So the other factor is temperature. So increase in temperature increases the resistance. As you can see, the atoms are vibrating with their mean amplitude, and this reduces the mean path of electrons. So when you plot a graph of resistance against temperature, there is that direct proportionality. However, in some materials, when you increase resistance, you actually reduce when you increase temperature, you reduce resistance in other materials. So different materials such as the semiconductors, the semiconductors such as the silicon respond differently with increase in temperature. For them, they reduce when the temperature increases. Why? Because most of the electrons are set into mobility within them, so they conduct electricity now. Remember, we have already some conducting electrons, so increasing the temperature, you're setting the mean path, or you are setting other atoms into vibration, and then you're creating space within the material. So the semiconductors, their resistance actually decreases with an increase in temperature. So let's move to the next. The examples, I will just go through them very fast. Look at what is given, cross-section area and length. They want us to find what? Resistivity. We substitute in the formula, we get our answer as 6 exponent negative 4 ohm meter. The second case, we are given area, standard unit, length, standard unit, resistivity. They want us to calculate a resistance. We substitute in the equation. We get the answer 0.0001 ohm. Electric circuit. This is a path followed by current. Without a circuit, then current does not flow. So we must have that circuit. Types of circuits include, we have open circuits. This is a circuit in which current is not flowing to the external circuit A. And then the closed one is the opposite, in which current is flowing to the external circuit. Let's see this. Closed and open circuit. I think we already saw it in the other part. Closed, electrons flow, so it's a complete circuit, so the bulb will receive current. So the external part is the bulb. Opening, incomplete circuit. You break the circuit, break the path. So we closed the open circuit. This is a circuit in which current is flowing or not flowing, depending on the case, to the external circuit. The external circuit here is what? The bulb. Note, a shorter circuit is a low resistance path for the flow of current, of course, after discovering the factor. It occurs when 2 points in a circuit are directly connected so that current flows through a shorter distance. This increases the flow of current, hence damaging the circuit. Oh, that is very true. Too much current in the circuit spoils the circuit. Electrical symbols, kindly take care on these symbols here. We have the standard resistor, the symbol and its name. This symbol here is a standard resistor, fixed resistor, adjustable. This one we use it in experiments, for example verifying Ohm's law. You have a switch, this is open, then when you are to close you make it complete. You have a dry cell, one dry cell. If there are two, they become a battery. We have a diode. We shall discover this in the next discussion. We have dry cell, more than two, the accumulator. We have an ammeter used to measure current, a galvanometer for showing the zero deflection depending on the setup, alternating current supply circuit, bulb or lamp. We have the capacitor. We have crossed wires that are not connected. Then we have connected wires, voltmeter, etc. So I have more than this, and for as per our scope, some of them will be discussed in the next chapter. Remember, this is just introduction to current electricity. We shall discuss power, we shall discuss very many things. And also as you get to A level, we shall discuss very many symbols as far as electricity is concerned. Ohm's law. It states that current flowing through a metallic conductor is directly proportional to the potential difference across its ends, provided temperature and other physical conditions are kept constant. Once we keep temperature and other factors constant, the other factors you saw area, other factors nature of the material, stated that the current flowing through that is directly proportional to potential difference. Meaning, if you increase the number of dry cells from 1.5 to 3, that is another second cell, or to 4.5, then you're actually creating more current in that circuit. That is what he discovered. And throughout his experiment, he came up with what we call the an experiment to determine Ohm's law. And in his discovery, he discovered that current gives a straight line from the origin when it's plotted against voltage, meaning they are directly proportional. So that's what he discovered, and he came up with that law. Please, this is the third equation. Be careful with it. We are going to use it also. Where R is the resistance of the conductor, and then V is the potential difference. We agreed the definition of the potential difference. Where I is the current, and then one of the examples, we are given the potential difference. No, we do not have a potential difference. We have the resistance in units of ohm, and then the current. I want us to find the potential. We use the very example, the very equation, substitute, find voltage, measured in volts, V. The second question, we are given the resistance and voltage. They want us to find current. Use the same equation. We substitute to get the answer as to. Next, here we are given resistance and charge flowing for 2 minutes. But remember, we agreed that current is the rate at which charge flows. So we divide and we get our current. They want us to find the voltage. So we use V is equal to IR after getting the current. So our voltage will 3. Voltage or potential will be 3 volts. They want the voltage. They are given current of 0.4 ampere and then resistance of 20 ohm. We still use Ohm's law. Get 8 volts. Next, we are given current of 4 ampere flowing through electric kettle with a PD across its end as 8. They want us to find what the resistance. Ohm's law still. We get resistance as 2 ohms. Experiment to verify Ohm's law. This one we shall even do it practically in class. Procedures. So the circuit is arranged as shown. Switch case closed. Let me just paste the procedures very fast. As we can see our circuit, we have a rheostat for adjusting the resistance. We have a resistor of the appliance. We have an ammeter to measure current, voltage across the resistor, voltmeter across the resistor to measure the voltage potential difference, and then the dry cell, a single dry cell, and the switch. So what happens is that the circuit is connected as shown below, switch case closed, and the current flows through the circuit. Read and record the ammeter and voltmeter reading I and V respectively. The rheostat is adjusted to obtain several values of I and V, that's the current, the new values of current and new values of voltage, and the results are tabulated. A graph of V against I is plotted, obtaining a straight line through the origin. A straight line is obtained showing that the potential difference V is directly proportional to the current. And that one vividly shows Ohm's law is valid. Shows that Ohm's law is very true. Limitations of Ohm's law. The law only applies when the physical conditions of a conductor are constant. What are you? You keep temperature constant, you come with the thing, and of which it is very, very hard to maintain some of these conditions constant. Otherwise, if you don't maintain the temperature, then Ohm's law is invalid. The law does not apply to semiconductors, e.g. diodes and electrolytes. Semiconductors like silicon, diodes, electrolytes do not actually correspond to this law, because for them they are not actually conductors. Ohm's law was done, actually did this law, but basing on a pure conductor. So it didn't put consideration of other conductors. Ohmic and non-ohmic conductors. I think that's why we have to discuss this ohmic and non-ohmic conductors. And then ohmic conductors are basically those conductors that obey Ohm's law. And then they include metals. Copper, of course, one of the best conductor of electricity. Iron, zinc, etc. When a graph of I against V is plotted, we get a straight line through the origin. Non-ohmic conductors, of course, these are conductors which do not obey Ohm's law. They include filament lamps, diodes, neon gas. They have different curves. They do not respond with that direct proportionality. When a graph of I against V is plotted, a non-straight line is obtained, meaning their response to voltage does not give a direct increase in current. On the other hand, a reduction in voltage does not imply a reduction in the current. So they behave differently for the case of their nature and then the materials in them. So some of the graphs are here. Take your time, observe them very well. Ohmic conductors, copper wire, zinc, we have a straight line through the origin. Filament, current increases with increased voltage until when it's maximum, and then starts to decrease. Semiconductors or diode increase, then they maintain steady voltage as current increases. As you can see, a thermistor behaves like a semi diode. Neon negatives and positives are variations in the voltage and current. Then electrolytes. So neon gas and electrolytes do actually have the same property. Circuits connection. Ammeter is an electrical device used to measure current in a physics laboratory. We know that one. An ammeter has a very low resistance. Why? Because we want current to flow through it such that it can be measured. So to allow all the current to be accurately measured without being affected by the resistance, so that one should be at your medulla oblongata. The low resistance assures that all the current to be measured passes through the ammeter without being opposed or resisted. The ammeter is always connected in series. Why? It is placed in the path of current, as you can see. Why is it placed in the path of the current? Because it's that very current we want to determine. So it is the same current that will pass through it, not across it. It should pass through it. Voltmeter. Still, it's used in the laboratory to measure the potential difference, or the PD, of voltage in a physics lab, in a physics experiment. For it, it has high resistance. Why? Because we do not want current to pass through it. We don't want current to pass through a voltmeter. So all the current should pass through the appliance. However, for it just measures the potential, the amount of energy required to push these charges from one end of that appliance to the other end. I mean, one end of the conductor to the other end. So its role is just to measure, not again to consume current. What are you? It has a very high resistance, so as to draw a very low current or no current from the source, thus not affecting the total current in the circuit. However, an ideal voltmeter is actually not there, because by default these voltmeters are made by connecting wires, using wires in them, and I doubt whether we have a wire with zero resistance. Ideally, we keep some of these factors constant. However, it should be calibrated in such a way that it has very high resistance. The voltmeter is always connected in parallel because we want to determine the potential difference across. If you want to measure the potential difference across the cell, across the appliance, then you have to measure, to connect it parallel with the source of current, as you can see. Resistors. A resistor is a device which opposes the flow of current in a circuit. In a circuit, resistors are either arranged in series or in parallel. Now this one is very important. As you are getting to this in-depth discussion on resistors, I want us to be so careful, because we are yet to make now recommendations to the required circuit arrangements of these appliances. So for that case, we shall take appliances as resistors, because they have resistors in them. They oppose the current flowing through them. So just in case you are given bulbs, maybe 3 of them, and you are to decide on the best way of circuit arrangement, then we shall use the knowledge of arrangement of resistors, and that will be either series or parallel, but all this will base on the results of the calculation, given the variables, given the values of resistance, and also the PD applied. Let's just have a look at this. What is a resistor? As you can see, we have different types of resistors used in different arena. This is a rheostat, adjustable. As you can see, the symbols are very, very clear there. Taking a case of a bulb, when you connect a bulb to a dry cell, it gives actually gets destroyed without a resistor. It just burns. But attaching a resistor, then you're trying to reduce some current. As you can see, energy is reduced once a resistor is applied. Without a resistor, so that's how a resistor works. It reduces the speed of flow of electrons. It reduces the speed of flow of electrons. They vary from one to another. Taking a case where we have a straight road, as you can see, without a block, vehicles are actually steadily moving. But for this case, when there is a block or kind of a stop, then vehicles do not move steadily. Take another case of this water flowing through a pipe. When we reduce the flow of water by actually pressing on the tap, the pressure reduces. So that is the same thing. Putting resistance like you are reducing the pressure. So when you put resistance in a circuit, you're actually reducing the current flowing through that. So register a significant small value of current. Register a significant small value of current flowing. So all these are resistors used in different gadgets for different purposes. But the most important thing is to minimize the flow of current, because excess current, we agree, damages the circuits. So to reduce this impact, we have to employ resistors. We have to use resistors. Types of resistors: standard resistors. These are resistors with known resistance. You will always find them in the lab. You always find them in the lab: 2 ohm, 5 ohm, 10 ohm, etc. Then variable, the ones we adjust. The ones we adjust. If I can show you in this video, they're of this caliber, that one. So this is what we call adjustable resistor, or the rheostat. These are resistors whose resistance can be varied by moving a slider. So as we move this slider, you actually reduce or increase depending on the demand. Let's start with the arrangement called series arrangement of resistors. Resistors are said to be in series if they are connected end to end, so that the same current passes through them. In series, the same amount of current flows through each resistor. The potential difference, or the voltage across each resistor, is different. There is always a potential drop across each. If there are two, those are two different values of PD, that when you sum up them, you get the exact PD from the supply source. The total voltage is equal to the sum of individual voltages across each resistor. That is very, very correct. Let's consider three, R1, R2, and R3 connected in series across a potential voltage this. As you can see, each resistor or each appliance has a voltage across it, meaning the total voltage V1 plus V2 plus V3 is equal to the applied voltage, and from Ohm's law we are actually going to substitute. The agreed voltage is equal to IR, and then for each case we shall substitute its current and resistance. It's the same current, so resistance varies at each stage. So IR is equal to IR1 plus IR2 plus IR3, pulling out currents, factorizing, we get current out, and we divide both sides by current. We remain with R is equal to R1 plus R2 plus R3. So effective resistance for series arrangement of of appliances, the resistors, bulbs, the fridge, and all those things that we use as electrical gadgets, their series or effective resistance is calculated by adding up the individual resistance. So that is the first equation that we should also take note as far as the arrangement of resistors are concerned. All electrical appliances, for example lamps, bulbs, it is connected in series, have the same amount of current flowing through them. Meaning when one gadget gets off, then the whole system is off, because it has a single direct flow of current. Note you should know. Parallel arrangement of resistors. Resistors are said to be in parallel if they are connected side by side, with their adjacent ends joined together at a common point. Note, in parallel, PD across each resistor is the same, because they have the same PD across, since they are joined side by side. So they have the same PD at the adjacent ends joined together. current flow in the circuit splits, and therefore current through each resistor is different. I think Kirchhoff's law comes in here, and then we discuss the Kirchhoff's law of algebraic sum of current at a junction. Total current is equal to sum of individual currents through each resistor. I think this is where we are applying Kirchhoff's. Consider three resistors, R1, R2, R3, connected in parallel across a potential difference V. As you can see that, we agreed that they will be connected side by side, and then we have a common adjacent ends where the voltage is to be tapped to close a circuit. So it is the same voltage, but as current is flowing, kindly allow me to do this. As current is flowing, this current splits, current splits. So at this point is what we call a junction. Kirchhoff came in and discovered something, and he said if you add the current, the total current leaving that junction, the algebraic sum of this current is equal to the current entering that junction. And that is very true, and we shall apply that in this context. So this is the simple arrangement, taking a case of 3 resistors, and you'll be given maybe 2, 3, 4, 8, 10, depending on the demand of the scenario. So from Ohm's law, we get to realize that V is equal to IR. So when I make current the subject, because I want to get the current for each such that I can sum up them. So when I make current the subject from Ohm's law, current is equal to V over R. Yes. So adding up the current total is equal to current 1 plus current 2 plus current 3. So in terms of Ohm's law, I will have V over R1 plus V over R2 plus V over R3. Pulling out V or factorizing V, I get V, dividing both sides by V, left hand side and right hand by V. Remember, 1 over R is equal to 1 over R plus 1 over R1 plus 1 over R2 plus 1 over R3. So that is one of the equations that we shall use as far as the arrangement of resistors. So we get to realize that for parallel arrangement, the effective resistance is the reciprocal of effective resistance is equal to the algebraic sum of the reciprocal of individual resistances. Note, for 2 resistors, of course that's an obvious thing, you'll get 1 over R1 plus 1 over R2 to take the LCM. Our main effective resistance is product over sum of those 2 resistors. Resistance of those 2 resistors. So to summarize everything on series and parallel circuits, let's just watch this video. As you can see, we have our dry cell, the battery supplying electricity, flowing in a single direction. That's direct current. And then a circuit is actually a path through which current flows. So that is a path. And when you break that, it becomes an open circuit. So taking a case where I have 2 bulbs, you can see current, they register the same amount of current because they are receiving the same current. For the other parallel, there's a breakdown in current, as you can see. So they receive different current, but current entering a junction is the same. R1, R2 series, R3, R4 series, but the combination gets a parallel. Series, then the effective from the source, currents flowing through R1 and R3 the same, then different from the one that's flowing from a combination of R3 and R4. Voltage, current, and resistance in series and the parallel circuits. Parallel circuits. We're just summarizing what we've been discussing. So we agreed voltage, current times resistance. If I want current, voltage over resistance, and if I have resistance, I need voltage over current. So for the series arrangement, you can see that as series, they receive the same current. Then parallel, different current but the same voltage. Then series, different voltage. So for this case, if you have R1, R2, they actually in series, they receive the same current but different voltage across each resistor. Different voltage across each resistor. So current is equal to supply voltage over effective resistance. So if I have 2, then I will have 0.25 ampere flowing through. Then if I switch the same into arrangement of parallel, then I need to first get effective resistance, where I get the product, since there are 2, product over sum. You add them, multiply them over their added values, and then you divide that by the voltage, divided by voltage. So V supply over R effective. In other words, if I have the current, I can find the voltage. If I have the voltage, I can find the current, etc. So we can see there's a potential drop across each resistor, V1, V2. However, they have the same current. V1 is equal to IR1, then V2 is equal to IR2. So when I have the values, I can calculate the V1. I can calculate the voltage across each resistor, across each appliance. So the V2 is IR2. I get 1 volt, 0.5. When I add them, I should get 1.5 for the standard cell. 1.5. So for the parallel arrangement, the same voltage is across them. So what we are going to do here is very simple. We shall use the same voltage, if it's 1.5, to help us find the current across through each resistor given the known resistance. And just in case you do not have the other resistor, for this case R1 is not known but R2 is given, so I will use the same voltage to determine that. We on series and parallel circuit. We repeat effective resistance R1 plus R2. That's for series. Then for parallel, since there are 2 resistors, I take the product over the sum. Product over the sum to get the effective resistance. For the case of bulbs, they receive the same current. Then that's for series. Then for parallel, they receive different values of current. Meaning the series, when you connect bulbs in series, when there is a circuit break in one, as you can see one is off, then the whole circuit is down. So it's quite dangerous to connect these gadgets in series, for one reason, that breakdown in one circuit, in one bulb, in one appliance affects the entire system. On the other hand, you can see one bulb is down but the other one is still working, meaning a breakdown in one does not actually affect the other. So the parallel circuit is advantageous for that very reason. For that very reason. Breakdown in one does not affect a breakdown in the other. So we will try this. As you're trying it, let's wait for the response. Can we confirm whether your answer or your response is correct? The current in this circuit, first circuit, is 2 ampere. We have the same resistors, the same voltage. We want to see the current. So for series we have 2 ampere. Then for parallel we have 4 ampere. So which one is the best in terms of maximizing current? Of course, that is the parallel. So parallel is very important for the case it gives the biggest value of current. And then for series, it is not very important because of small value of current, and also a breakdown in one circuit affects the whole. A breakdown in one appliance affects the whole circuit. So the two things are very different, and we can apply this knowledge in real life as far as connection of appliances are concerned. So we shall use the resistors as the real life appliances we have, and we shall examine very many scenarios that require us to pick the best connection that suits the demand of the client. So some examples are down here. We shall just use the same concept of parallel 3 to find. Roman 1, we are just adding. Roman 2, we are adding 4 and 2, then they become parallel with 3, and then we get the effective as 2 ohm. Roman 3, 3 and 2 are parallel, we need to get their effective, then we add to get 5.2. Next, 4, 5, 2 are parallel, we take the reciprocals as usual, then we add the results, and then we get effective of 5 ohms. Roman 5, 3, 4, 7, 3 and 4 are in series. When I reduce them, I get 7. 3 and 4, 7. Then 7 and 7 parallel. I reduce them, I get what we call parallel, that is to be in series with a 3 ohm. So the effective will be 6.5. Next, I think this is a series because they receive the same current. 30, 10, you just add them. Second last, 63, they are in parallel because they receive different current at the junction. As you can see, at this junction, where are you? At this junction, as this current is coming, another proportion goes to 6 and another one goes to 3. So that's why they are in parallel. So once there is a breakdown, once there is a break or a split in the current entering a junction, then for that circuit it is actually arranged in parallel. So let's finalize the last one. Of course, the effective is going to be 2 ohms. Then the last circuit seems to be complicated a bit, but you can break it in different ways. 6 and 4 can be parallel, they reduce to 1. And then how about starting with this? If you look at 1 and 6 parallel, there are very many ways of reducing this depending on your choice. So if you look at 3 and 6, they are in parallel, but when you reduce them they become series with 1, so that's why we are adding. Then if you look at 12 and 4, they are in parallel, so when you reduce them they become 1 that you have to add. So what I'm meaning is, if you look at this and this, they are in parallel. When I reduce them, I get 1 in series, so I can add them. Then when I reduce this with this parallel, 12 and 4 parallel. So the result, I add them, they become series. So that's what I'm meaning. So you just use the appropriate formula for each case. So the activities down there that I will want you to try out. 1, 2, 3, 4. Each is for 5 scores. Then you have your 20 scores there. Otherwise, there's arrangement of cells. So cells can be arranged in series and parallel because they are the ones providing us with EMF. So this EMF can be arranged parallel or can be arranged in series. So for series arrangement, we actually connect the positive terminal of one cell to the negative terminal of the other. The total EMF of the cell is equal to the sum of individual EMFs. So these EMFs keep accumulating on adding more dry cells. That's why when you get a bulb and you connect, keep increasing the number of dry cells in that circuit, but for the series arrangement, the brightness of the bulb increases, meaning more current is produced or is given out. When you consider 3 cells of EMF E, internal resistance R connected in series as shown, you get to realize the total EMF is adding up them, and also since they are in series, then we use the formula for effective resistance as addition of the individual internal resistances. Individual internal resistance. Parallel arrangement. So if the positive terminals of the cells are connected to one point and the negative terminals are connected to another point, then that's when we have the parallel arrangement. The total EMF is equal because it has a one potential across each. So they share the same potential. So the total EMF is equal to one of the EMFs of the cell. We consider 3 of EMF, internal resistance R. As you can see, they have the same voltage E. So E is equal to E1 is equal to E2 is equal to E3. And then since they are in parallel, we use the knowledge for effective resistance for parallel connection, where we take 1 over effective internal resistance equal to the individual sum of the reciprocal of individual internal resistances. So the circuit equation, if you look at that circuit equation, you have a dry cell connected to an appliance of internal resistance R. So effective resistance is internal resistance plus external resistance because they are in series. And then using Ohm's law, we substitute V is equal to IR, but the voltage is EMF E. And then current remains, but effective resistance will be addition of R plus small r. So this is what we call the circuit equation that helps us to find EMF, electromotive force, in a dry cell. So the terminal PD is the voltage across the terminals of a cell when current is being delivered to an external circuit. Why do you think that the terminal PD is always less than the actual EMF of a cell? You find that the EMF of a cell is actually 1.5, but it does not actually give all of it as 1.5. Why? This is the reason. The terminal PD is always less than the EMF because of the opposition to the flow of current within a cell, that is internal resistance. I remember telling you about the other opposition projected to the electromotive force, sending the electrons from the positive plate to the negative rod. So that opposition reduces the EMF, reduces the what? The voltage. That is it. Examples, we are still going to use those equations for EMF. If they are in series, we just add them. Effective resistance, we add them. If they are in parallel, the first three, we add them. Or if they are in parallel, okay. So this is a mixed thing, parallel and series. So this one is in parallel, so they will become 1. Then this one here, they are in series, they become 3. So if they have the same voltage, these are 4 dry cells. So that's why we are having the 4 dry cells. So for total resistance, you need to be careful. These ones here are in parallel, so I take the sum of the reciprocal of individual resistance, and then after getting that, I add to this individual. I just keep adding them, so that's why I'm getting 6. And then the next, for this case, we have 2 dry cells. Together, since they are in parallel, they will be of 4.5 volts, and then the internal resistance 0.5, 0.5. So this parallel will give us, since there are 2 resistors, we shall use the product over sum to get the effective internal resistance. Then for that case, we shall be in position to calculate the current, because we have an external rod, effective resistance inside. Then we use the circuit equation to substitute. Then the ammeter reading, or the current, will be 2 ampere. The current will be 2 ampere. 2 ampere, 2 ampere, 2 ampere, 2 ampere. So some worked out examples are here still. We have 8 dry cells. Effective EMF is, of course, since they are of identical value, we just multiply times 8 and it gives us 12. And then internal resistance inside them, still we shall just multiply. We consider 2 and 3 being in parallel. We treat that one into 1. Then the result gives us a series arrangement with the 1 and the effective of internal resistance of the tri cells. So the final thing gives us a current of 4 ampere, given that the voltage, where is the voltage? Yes, the voltage is already there, which is 12 volts. The next question, we have a battery of 6 volts, because each dry cell is 1.5 and there are 6. Then we have bulbs. 2 bulbs are in parallel, meaning their effective resistance, I need to take the summation, product over sum, because there are 2. Then the result go into series with the other one. Then I add them. However, I need to get the effective resistance for this circuit equation, given that the internal resistance of the dry cells is under consideration. That's why we need to add that 0. So final result, I get 5 amp.